Diamond is the hardest natural material on Earth. Nothing you own can scratch it except another diamond. Graphite is so soft it flakes apart if you press it against paper, which is exactly why it's the lead in your pencil. And yet chemically, they are the exact same thing. Not similar, identical. Both are pure carbon, nothing else, not one different atom between them. So where does the hardness go? This is symmetry. Let's find out how the exact same atom builds two materials with completely opposite properties. Before anything about structure, the composition has to be settled first. Diamond and graphite are both built from carbon, and only carbon. No other element is involved in either one. Break a diamond down to its individual atoms, and every single one is carbon. Break graphite down the same way, and every single one is also carbon. Not carbon plus something else in one and pure carbon in the other. The exact same element, atom for atom, with the exact same 6 protons, the exact same electron count. Nothing chemically different about a single particle in either material. If the atoms themselves are identical, whatever makes diamond hard and graphite soft cannot come from the atoms at all. It has to come from something else entirely. When the same element forms more than one distinct structure, chemists call the different versions allotropes. It's not a mixture, and it's not a compound with something else mixed in. It's the same atoms, rearranged into a different repeating pattern, the way identical bricks can build a wall or a tower. Same brick, completely different structure, completely different strength. Carbon happens to be one of the most dramatic examples of this in all of chemistry, and diamond and graphite are its two most familiar results. Carbon isn't the only element that does this. The oxygen you breathe is 2 oxygen atoms bonded together, but rearrange 3 oxygen atoms into ozone instead, and you get a completely different gas, with a different smell and a very different reactivity, still nothing but oxygen. Phosphorus does something similar. White phosphorus catches fire spontaneously in open air, while red phosphorus sits safely on the strike strip of a matchbook, both built from nothing but phosphorus atoms. Carbon is simply one of the most dramatic examples of a pattern that shows up across the periodic table. Start with diamond. The story of its hardness is entirely a story about how each carbon atom chooses to connect to its neighbors. In diamond, every single carbon atom forms a strong bond to 4 other carbon atoms, arranged so the angles between those bonds are all identical, pointing toward the corners of a tetrahedron, spread out symmetrically in 3 dimensions. There's no direction a bond doesn't reach toward. Every atom is fully, completely wired into its neighbors on every side, above, below, and all around. This 4-way tetrahedral bonding pattern is the entire seed of everything that makes diamond behave the way it does. Repeat that 4-bond pattern outward from every atom over and over, and the structure doesn't stop. It keeps extending in all 3 dimensions, atom locking into atom, forming one single, continuous 3-dimensional lattice. A diamond you can hold in your hand isn't a pile of separate molecules sitting near each other. It is, structurally, one enormous molecule, every carbon atom directly wired to the next, through real covalent bonds, running uninterrupted in every direction through the entire crystal. Try to scratch or deform that structure, and there's no gap, no weak seam, no direction where the atoms are only loosely connected. Any force you apply has to fight through actual covalent bonds, the strongest ordinary connection 2 atoms can form, running through the crystal in every possible direction at once. That's the entire reason diamond is so hard, not a special ingredient, just an unbroken 3-dimensional net of the strongest bond chemistry has to offer. On the standard scale scientists use to rank mineral hardness, diamond sits at the very top, a perfect 10, the reference point everything else gets measured against. That same rigid, fully wired structure also happens to pack carbon atoms about as densely as they'll go. Every atom pulled in tight by 4 strong bonds, reaching in every direction, leaving almost no empty space anywhere in the lattice. It's no accident that diamond only forms naturally under enormous pressure, deep within the Earth's mantle, conditions that force carbon atoms close enough together to lock into this compact arrangement in the first place. At ordinary surface pressure, carbon settles into a much looser structure instead. The numbers show it directly. Diamond packs in at roughly 3.5 grams per cubic centimeter, while graphite manages barely 2¼ nearly a third less dense, purely because its layered structure leaves so much more open space between the sheets. Now take the same carbon atom and let it bond differently. Graphite starts from the same starting material and ends up almost nothing alike. In graphite, each carbon atom bonds strongly to only 3 neighbors instead of 4, and those 3 bonds all sit in the same flat plane, spaced exactly 120 degrees apart, forming a perfect hexagon shape repeated over and over. There's no 4th bond reaching up or down out of that plane. Every atom commits its strong covalent bonds entirely sideways, within a single flat sheet, and nothing holds it strongly to whatever sits above or below. Repeat that 3-bond hexagon pattern across millions of atoms, and the result is a single flat sheet, a honeycomb of carbon stretching out in 2 dimensions, strongly bonded within itself the whole way across. Inside that one sheet, the bonds are every bit as strong as the bonds in diamond. This layer, taken completely on its own, is not a weak material at all. The weakness shows up between the sheets, not inside them. A piece of graphite is many of these honeycomb layers, stacked directly on top of each other. But the connection holding one layer to the next is nothing like the strong bonds inside a sheet. It's a much weaker attraction, the kind that exists between any 2 neutral surfaces sitting close together. Nowhere near strong enough to compare to an actual covalent bond. Graphite, structurally, is less like one solid block and more like a tall stack of separate sheets of paper. That one structural difference, bonds in 3 dimensions versus bonds confined to flat sheets, explains the entire contrast in hardness. Push sideways on a stack of graphite sheets, and because the layers are only weakly attracted to each other, they slide, one whole sheet gliding past the next with very little resistance. The strong bonds inside each sheet never have to break at all, only the weak attraction between sheets gives way. That's what softness actually means here. Not weak atoms, not weak bonds, just an entire plane that's free to slip. This is exactly the mechanism behind a pencil. Pressing graphite against paper shears thin stacks of these sheets apart, and because sliding takes almost no force, entire layers flake off and cling to the paper's rough surface, leaving a dark streak behind. Every pencil mark is a smear of graphite sheets that slid loose from the stack they used to belong to. The name is actually a leftover mistake. Early miners who found graphite assumed it was a form of lead ore and called it plumbago, from the Latin word for lead. Pencils have never contained any lead at all, just this one particular structural arrangement of carbon. Apply that same sideways push to diamond, and there's no equivalent weak seam anywhere to exploit. Every direction inside the crystal is reinforced by the same strong tetrahedral bonds, so there's no plane where atoms are only loosely held and free to glide. The push simply has nowhere weak to go. Same kind of force, same element underneath, but one structure offers an escape route and the other offers none at all. The exact same structural difference also decides something that has nothing to do with hardness at all: whether the material conducts electricity. Each carbon atom in diamond uses all 4 of its outer electrons to form those 4 strong bonds, and every single one of those electrons stays locked in place, holding a specific bond between 2 specific atoms. There's nothing left over, no loose electron free to wander through the crystal. Without mobile charge to carry a current, diamond simply does not conduct electricity. An insulator built from the very same atom that, arranged differently, does something else entirely. In graphite, each carbon atom only uses 3 of its 4 outer electrons to form its 3 in-plane bonds. That 4th electron doesn't belong to any single bond. It spreads out across the entire sheet, free to move alongside countless other leftover electrons from every other atom in the layer. That shared mobile sea of electrons is exactly what a current is. Graphite conducts electricity easily along its sheets. For the same underlying reason, diamond can't conduct at all. How many electrons got left over once the bonds were built? Here's a genuine surprise hiding in diamond's own structure. Despite being an electrical insulator, diamond is actually one of the best conductors of heat known. Better than most metals, the same rigid lattice that locks every electron firmly in place also transmits vibration extremely efficiently, atom to atom, straight through those same stiff bonds, carrying heat through the crystal without needing a single electron to move at all. Electricity and heat, it turns out, don't travel through a material by the same rule, and diamond happens to excel at one while completely failing at the other. That property is exactly why real diamond, or lab-grown crystals with the same structure, gets used to draw heat away from high-power lasers and electronics, doing a job ordinary metal heat sinks can't match, entirely because of a structure that has nothing to do with sparkle at all. Carbon's flexibility doesn't stop at two shapes. Rearrange the same atom a little further and stranger materials appear. Peel a single honeycomb layer away from the stack, completely isolated, and you get graphene, just one sheet thick. Freed from the weak neighbors above and below, that lone layer turns out to be one of the strongest materials ever measured for its weight. Exactly what you'd expect once you remember the bonds inside a single sheet were always as strong as diamonds. Graphite was never really a soft material. It was a strong material, stacked in a way that made the whole pile easy to shear. Isolating that single layer for the first time, using nothing more exotic than ordinary sticky tape to peel it away one sheet at a time, won its discoverers the Nobel Prize in Physics in 2010. Curl that same hexagonal sheet into a closed sphere, and you get a buckyball, a soccer ball-shaped cage of exactly 60 carbon atoms. Roll it into a cylinder instead, and you get a carbon nanotube, prized for a strength-to-weight ratio beyond almost anything else known. Diamond, graphite, graphene, buckyballs, nanotubes, 5 wildly different materials, 5 wildly different sets of properties, and every one of them made from nothing but carbon. So the real answer was never hiding in the atom. Carbon is carbon, everywhere, in every one of these materials. What changes is entirely the geometry, how many neighbors each atom bonds to, and in what shape. Hardness, softness, conducting, insulating, all of it falls out of that one structural choice, repeated billions of times over. Chemistry's identity was never just about which atoms you have. It's just as much about the exact shape you arrange them into. So diamond and graphite are not two different substances that happen to share an ingredient. They are the exact same atom, telling two completely different stories depending entirely on how it's arranged, locked into a rigid, three-dimensional net, or stacked as flat sheets that slide. One structural choice built the hardest natural material on Earth. The same choice, made differently, built the material inside your pencil. If you want more ideas like this, explained from first principles, subscribe Symmetry. See you in the next one.